In this video, we will cover 3 different techniques for tuning hyperparameters in an XGBoost classifier. The XGBoost is one of the most popular machine learning packages out there for supervised problems. In this video, I will introduce the concept of what is a hyperparameter, and then I will describe the 3 different techniques that we will work through here. Now, these 3 different techniques will include grid search, randomized search, and Bayesian optimization. So now let's start off with a description of what exactly is a hyperparameter. So hyperparameters are input parameters to a machine learning model that are set by the programmer. So these differ from the model weights that are learned by the machine learning algorithm. These are a different set of parameters that cannot be learned from the data. Instead, a programmer has to explicitly set these. Now, the act of hyperparameter tuning is to come up with a configuration of these hyperparameters that are most ideal for the problem at hand. And so normally a hyperparameter tuning algorithm is, you can think of it as a meta-algorithm. It's an algorithm on top of our machine learning model that tries to find the ideal set of hyperparameters for the problem that we are working on. Now, in our case here, we'll be looking at a XGBoost classifier, and I selected out 5 specific hyperparameters that are typically very important to tune right in order to get the best performance out of your XGBoost classifier. So these include the number of weak learners, the learning rate, maximum depth, and the L1 and L2 regularization. So let's take a look at each of these quickly. So first off, the number of weak learners is simply the number of elements we have in our ensemble. So as I mentioned in a previous video on XGBoost, XGBoost is a boosting algorithm, and just like any other boosting ensemble, it's a collection of different, much simpler machine learning algorithms. These are called weak learners, and they're all grouped together and function in a cohesive way in order to form a very powerful estimator. Now here I have a depiction of a very simple boosting algorithm. So here we only have 3 constituent trees, or very simple trees, the decision stumps. And so in this case, the number of weak learners is 3. But this number is arbitrary. You can set it to be pretty much anything you want in your estimator. So this is something that will be important for us to set correctly. Now the next parameter is the learning rate. And this is important for determining how fast do we update the model parameters during training. So here we have a visualization of a loss function, and it's actually it's a 2D surface plot of the loss function as a function of 2 of the model parameters in our algorithm. And the orange arrows indicate the steps that are taken by the learning algorithm as it tries to approach the minimum here. And so the learning rate just defines the size of these steps that we take in the model weight space. The next hyperparameter is the max depth, or the maximum depth of our trees. So for each constituent tree in our ensemble, we can define how complex each one of those trees can get. Now in this case, in this visual, we have 3 different layers to our tree, and those are all color-coded. So we have the root node that's in orange, then we have the second layer that's in blue, and then the final layer is in green. So this tree here has a depth of 2 because there are 2 separate sets of splits in the tree. But this again can be an arbitrary number. It can be anywhere from 1 to any positive integer. So this is again something else that we'll have to set correctly. So with L1 regularization, what we have is an additional term to our loss function. Now here on the right-hand side, you see this additional term. It's the lambda with the sum over all the model weights from I equals 1 to n. Now this summation is done in terms of the absolute value of the model weights. So this regularization term is simply in terms of just the absolute value of these weights. Now the effect of L1 regularization is to penalize very sparse features in our input feature set. So in effect, what L1 regularization does is feature selection. It removes out non-informative features and just retains those that are most relevant for solving our problem. And in effect, this simplifies the overall machine learning problem that we are trying to tackle. L2 regularization is similar to L1, except that instead of looking at the absolute value of our model weights, we look at the squared model weights instead. Again, like the L1 regularization, we tune this with the lambda parameter. And this is in fact what we're setting when we do hyperparameter tuning with these regularization terms. And what L2 regularization does is it tries to minimize model complexity. So models with larger weight values will tend to be more complex. And so with this type of regularization term added on, we penalize that effect and try to keep the model as simple as possible. The reason for this is to improve how generalizable our trained model will be. So that's really what we're aiming at here. So now that we've covered all the hyperparameters that we'll be looking at in this video, let's briefly go over the 3 different methods we'll be exploring here. So the first is grid search, and this is probably the most straightforward method for doing hyperparameter tuning. And this is just an exhaustive search, very mechanical, over all the possible combinations of input parameter values. So with grid search, we define, just in a list, we define a set of possible values that we want to investigate. And we define these lists for each of the hyperparameters we want to look at. And then we essentially loop over all the combinations, evaluate how well our model performs, and then select out or retain the configuration of hyperparameters that ends up yielding the best result. So the downside of grid search is that this process can be quite expensive in terms of computational resources and time. So grid search typically takes quite long. Its strength is that it's very simple to understand and implement. Now the next method we'll be looking at is randomized search. Now in this case, what we do is random sampling over the possible parameter values. Now, we can do this in one of 2 ways. We can either define the parameter values as a set of lists, a list of parameter values for each hyperparameter, similar to what we did with grid search, or we can define a probability distribution. And then the randomized search will just select out random samples from that distribution. Now, the strength of randomized search is that it can run quite a bit faster than grid search. So that's the main advantage for using that approach. Now, the last hyperparameter tuning method I'll be looking at is Bayesian optimization. Now, this technique takes advantage of Bayes' theorem to make informed decisions at each iteration in the algorithm. So whenever we select out a new set of hyperparameters that we want to test out, we don't just do that at random the way we do with randomized search or in a mechanistic way that we do it with grid search. Instead, Bayesian optimization takes into account the previous iteration in the algorithm, the results from that previous iteration, to inform what the next set of parameters to be tested out, what should those values be. And so in this case, we can actually arrive at good results in much less time. So this is a very attractive option in terms of finding an ideal set of hyperparameters in the shortest time possible. So now we can jump into a Jupyter notebook and work through the 3 different hyperparameter tuning techniques that I covered in the previous slides. And before we begin, I just want to emphasize that this notebook is available on my GitHub. I will include a link to this notebook in the description below. So let's first start off by importing all the packages that we will need for this experiment. Okay, and the next step will be to create our data. Now here I'm going to be making use of the make classification function available from scikit-learn. And this will entail, or the data we will create will involve 1,000 samples. I'm going to create 100 predictive features, 60 of which will be informative. The target label will consist of 2 classes with weights 0.4 and 0.6 respectively. And throughout this notebook, I'm going to be setting the random state. That's just to make sure that we have reproducible results. Once we have our data, I'm then going to do a train test split, where 20% of the data will be allocated for testing. So we will do all our hyperparameter tuning on the training data set, and then with the best estimator that we get out of that, we will evaluate it on the test set. So now let's run this cell. Okay, so the first thing I want to do is create a baseline. And the purpose of this is to evaluate what effect does our hyperparameter tuning have on the model performance. So for the baseline, I'm just going to be using the XGBoost classifier with its default hyperparameter values, except I'm going to be setting the random state again. So let's just run this cell and see what we get. So okay, we see that already with the default values, we have a pretty well-performing classifier. We have an accuracy score of 0.83, precision of 0.81, recall 0.91, and an F1 score of 0.86. So let's see if we can improve these values through hyperparameter tuning. So the first thing I'm going to do is run grid search. I have defined in this dictionary called parameters all the possible values that our hyperparameters can take on. So this includes our number of estimators, or this is the number of weak learners in the ensemble, and the values that it can take on are included in this list. Likewise, I've also defined the values for the learning rate, the maximum depth, the reg alpha, and this is for the L1 regularization, and the reg lambda, which is for the L2 regularization. So grid search is going to just iterate through all possible combinations of these values and then come up with an ideal set of parameters and an ideal or best performing estimator out of this. I'm also going to be timing how long it takes to run this technique, and I'll do the same thing for randomized search and the Bayesian optimization, just so we have another point of comparison between these methods. So let's go ahead and run this cell. Okay, we can see that the grid search is finished, and now we have a set of hyperparameters that the algorithm has selected out as being ideal. So now let's test this out on our test set to see if the model performance improves. So okay, we can see that the results haven't changed significantly, although if we compare it to the baseline, we can see that the F1 has gone down a little bit with comparison to what we get out of grid search, and the same with the accuracy score as well. So the accuracy score is 0.81, whereas just with the baseline we have 0.83. So part of the problem that we have here is that with grid search we have to define the discrete values that the hyperparameters can take on. There's no possibility that the algorithm can, say, pick a value between any of these values. So we can't pick, say, 75 as a value to try out for n estimators, for example, because it's not defined in the list. So this lack of refinement could be one reason why we actually see a little bit of degradation in the model performance from doing grid search. We can also see that the computation time took about just over 300 seconds. So let's see if we can improve upon this by doing randomized search. Now with randomized search, the key difference here is that instead of defining the hyperparameters, or instead of defining the values the hyperparameters can take on through a set of lists, instead we're going to assign a probability distribution to each of these hyperparameters, and we will draw out samples from those probability distributions. So for the integer hyperparameters, and that includes the number of estimators and the maximum depth, I'm going to be drawing from a Poisson distribution. And for the learning rate and then the regularization terms, I will draw from uniform distributions. So these will all be fed into the randomized search CV object. This is also available from scikit-learn. And I'm going to run this for a total of 100 iterations. So this basically controls for how long the algorithm will run for. Like before, I'll also be timing the computation, how long the computation takes. So let's go ahead and run this cell. Okay, so we can see that the algorithm has finished, and again we have a set of hyperparameter values that have been returned. We can see that because we're drawing from a probability distribution, we're able to get very precise values for these hyperparameters. So let's now test out the results on the test set to see what we get. Okay, so the first thing that jumps out is that the values are quite a bit better than with the grid search. So the accuracy score now goes back up to 0.83. So that's better than grid search, and it's right back to where our baseline was. And if we go back down, we can also see that the F1 score is actually a bit better, and the recall specifically has improved. So here we have a recall of 0.94, and if we go back up to our baseline, it's 0.91. So actually this improved. The precision degraded just a little bit, and that's why the F1 score basically stays the same as the baseline. But yeah, for your problem, if the main thing is the recall, then this result is pretty nice. And of course, the computation was a lot quicker than the grid search. So now let's see if things could get better through our last method that we'll try out, and that's Bayesian optimization. So here, we're also drawing from probability distributions like before. However, in this case, because these probability distributions are set up in a Bayesian context, so we have a prior distribution, and then that is going to be multiplied with our likelihood to yield the posterior distributions at each iteration. So at each iteration, we are going to take into account the effects of the previous iterations. And in this case, we hope to be able to get better hyperparameter values for less time. So in this case, I have defined uniform priors for the number of estimators, the maximum depth, hyperparameters, and then I'm using the log normal prior for the learning rate and then the regularization terms. Like before, I feed that into our object that's going to carry out the hyperparameter tuning, and that is the Bayes search CV object. And I'm going to run this for just 5 iterations. So let's see how well our results can be from this. Okay, so the algorithm has run. We have a set of hyperparameters, and now let's test it out on the test set. So here we can see that actually the results have improved just a little bit. The accuracy score is again the same as with the baseline and with randomized search, but the F1 score is actually improved, and that's because the precision score has gone back up to what the baseline was, but the recall has still improved. So overall, our F1 score has gone up a bit. And also, the thing that stands out is that the computation time is only 11 seconds. So it's by far the fastest technique out of all 3 tried. Now you can continue to play around with this. Again, feel free to make a copy of the notebook and experiment with different distributions, different ranges for the parameters. You can take this pretty far and explore what can be done for hyperparameter tuning. So that concludes this video. I hope you got some value from it. If you like this video, please like and share this content. Also feel free to subscribe to my channel. It's always appreciated. And I hope to see you in the next video.